So do you see my screen now? I believe you see it. I believe you see my screen now. Anything? Charts. Okay, you can see. Okay, great. So let's see what we have. Let's see what we are going to do now. Basically, and here is our presentation and what I want to show you. So okay, we talk about Fourier transformation, right? So basically, and remember last time I wrote these two formulas, Euler formulas, and basically that's what I believe you know this, but that's what I wanted to remember. So what is Fourier transformation? What is Fourier analysis? Please, again, it's not easy topic, but you have your textbook to read. I want you to get some very basic idea of what we are doing. So let's say like this. We have our space. What is our space? In our space, what are typical dimensions? It's mass, length, time, temperature, and so on. Here we'll talk about length scale and time scale. So in our space, we measure something, right? We measure how you change, how you move, how particles move, how people move with respect to time and distance. So for simplicity, for some reason, we will go to something that we call Fourier space. In this Fourier space, instead of lengths, instead of coordinates, instead of x1, x2, x3, we will have wave numbers, k1, k2, k3. Everybody remembers what is wave number? It's inverse of wavelengths. If you have vibrations, k is 2 pi over lambda, so we have these wave numbers. Instead of time, in this space, again, easy way to deal with will be frequency. So why we need it? So what is the idea about this transformation? Why we do it? Let me say like this. Assume you need to do something. Let's say you need to repair a car, okay? Or you need to repair some device, your laptop, for instance. So what you can do? There are two ways what you can do. You can repair it yourself. It will be straightforward, but it will take time and maybe you don't know how to do it. That's one way. But there is another way. You may find somebody who knows how to repair your laptop. So what you will do it? You will ship your laptop to that person. This person will do everything for you, okay? And then somebody will send it back to you. It will cost more. You need to ship it. You should pay maybe for the service. But do you agree that this repair master, he knows better what to do than you? So that is the idea of Fourier space. When we want to solve the problem, when we want to solve our equations, what you do? Instead of solving them in our space, we do a transformation. So you move your problem, you pack it, and move it to Fourier space. In this Fourier space, luckily, somehow, it's easy to solve these problems. Why? It's another story, but believe me, it's true. It's not easy to go there. Transformation is costly, but in that new space, problems are easy to solve. So you fix your problem, you fix your repaired laptop, and then you shipped it back to our space. Does it make sense? Does it make sense? I believe so. That's why we introduce it. So now, so what is the space? So how to make this transformation? Here it is. So let's say in our space, I will talk now about one-dimensional space. So I have some function f, which is a function of x. Let it be anything. It can be velocity, it can be length scale, it can be something. So I will do transformation. So instead of my function f of x, I will have its image, its transform, which will be like this, which will be wave, it will be f of wave in k space, a function of k, or wave number, and it is defined like this. It will be f of x u minus ikx dx. So you may realize when you integrate, as a result of this integration, you integrate it over dx. So the result of this integration will be function of k. Do you agree with this? Do you understand this? Is it trivial? That's what you do. Again, so everybody remembers that what is E minus IKX? Everybody remembers that this is classical formula, or the formula that e to the power iy, it will be cosine plus r sine. So generally speaking, we deal with complex variable. So even if our space, you deal with real number, real variable, in Fourier space, you will deal with a pair of sine and cosine. Does it make sense? That is our convention. And later, when you do the work you need, you will make inverse transformation. So how inverse transformation will look like this. So if I have this function f of k in k space, sometimes we call it k space, Fourier space, I can do this integration vice versa. And then I will have what? I will have function of x. So please understand, when you do this integration, you integrate over x to get a function of k. Here, you integrate over k space to get a function of x. Does it make sense for you? I hope so. Sometimes, I told you last time, sometimes in some textbooks, you want to, so here we have like this, in direct transformation, you have coefficient 1 over 2 pi, and here you don't have this coefficient. In direct transformation, you have minus ikx, in inverse, you don't have it. Sometimes people want to make it weighted and symmetric. So in some textbooks, you will have the following. You will see that Fourier transformation looks like this. So you have root square of 2 pi. And then in inverse transformation, you will also have root square of 2 pi. This is just a question of coefficient. It does not change problem much, it's just a question of factor. But you realize. Why we need it? Because you can easily check, and by the way, that should be actually a good problem for you to solve. I do recommend you. So definitely, how this factor 2 pi appears. So if you integrate, you should come to the coefficient of 2 pi. So I do recommend you to do the following. You can do it. So please, if you consider this equation, for instance, what you can do, take this function, okay? Take this function and substitute it here, okay? Substitute it here. And take this integral. When you take this integral, your result should be 2 pi. That's why we introduce this coefficient to have the identity. Does it make sense for you? I believe so. That it is. That's why we need it. That's why we introduce these values. So now, a couple of things. So why we talk about this transformation? What is nice about Fourier and whatever? So why it's like this? Very nice. Because you remember this formula. So in fact, when you have complex variable, you deal with pair of sine and cosine. And basically, I believe everybody knows what is Fourier series, Fourier coefficients, right? So basically what you do here, why we call it spectral analysis. So basically what you have in Fourier space, instead of your function, you split into the basis. And what is the basis? So for instance, you know, there are polynomial decomposition, what we call Taylor or Maclaurin series. But that's something that is not very nice because different terms are not of importance. When you have like some kind of white noise, when you have some kind of set of frequencies, the key point that you want to split into bases, into harmonics. So that's what allows to do. In Fourier space, you instead of your complex function, you will have a set of harmonics. Why? Because of the following. So that's what we are doing. So transformation in Fourier space is actually dealing with series of harmonics. Now, and basically you realize that left-hand side, this is classical definition, whatever you have here, it's exactly up to the coefficient. And why we need this exponent? Because you remember what is classical item of exponent. Please realize why we need it. Why we need it, especially in fluid mechanical problem. What is good about exponent? What is good about exponent?
its derivative is itself.
Exactly. Exactly. Like in old joke that exponent is not scared to be differentiated, right? So basically, yes. So two things. If two things that if you differentiate or integrate exponent, it will be the same exponent. So it's invariant with respect to differentiation or integration. And second, which is related to this, that exponent or that product of exponents give you some exponent of sum, right? Like here. Why it's so important? Because what difficulties we face in fluid mechanical problem? They integral differential and they are nonlinear, correct? Remember the first lecture when we introduced Reynolds number, we say that what is big problem with turbulence? Because we have convection term. If there was no convection term, everything would be linear and nice. But we have convection term, nonlinear term, which is a product, and we cannot resolve it. So product in Fourier space will become summation. So if I have one term, a to the exponent of a, and then I have exponent of b, so their product will become exponent of a plus b. So product will become summation in Fourier space. Is it nice? Is it easy? That's why. Another point, differentiation will be the same. So instead of taking differential of time, you will multiply by frequency. Instead of taking gradient, which is not easy, especially 3D gradient, you will have multiplication of wave number. That's why our basic equation we deal with, Navier-Stokes equation, even continuity equation plus energy equation, they look really nice in Fourier space. In Fourier space, you switch from gradients, from differentiation to multiplication, and that makes it easy. And in nonlinear terms, appear split through summations, like here through set of harmonics. So each transformation it's costly, but when you do it, it becomes easy. So like I tell you example with when you repair your laptop, right? So it will take a lot of effort and time to find somebody who can repair it, but this person just make 3 shifts of buttons and it's repaired. Does it make sense? And then you go back and you have your laptop in your space, which is fixed. Well, this is, does it make sense? So that's what we are doing. That's why we need, and that's why how we introduce spectral density. And why I'll give this analysis, because typically it's not very related to what we want in this class, because next we'll talk about Kolmogorov spectrum. And in Kolmogorov spectrum, its key point is spectral density. And spectral density comes directly from the idea of Fourier transformation. Because what is spectral density? It's counterpart of energy density in Fourier space. So no question about this slide? Okay. Okay, let me go to next one. So, but what I discussed here was actually more or less simple. Why? Because this was one-dimensional. In fact, we deal with three-dimensional features. So in fact, when you do this transformation, so our general expression should be like this. Okay? So basically it's like this. So in fact, I have three-dimensional features. So I should integrate over x1, x2, and 3. So it will be like this. Integral, or it's volumetric integral. So basically, if I have my function of x, its Fourier transform will be this one. And here I have 2 pi cubic, right? While inverse transformation will be the following. Will be like this. Again, here x and k are vectors now. Okay, so it will be k1 x1 plus k2 a2 plus k3 a3. Again, sometimes people, to make it symmetric, and you see this coefficient. Now instead of 1 over pi, you have 1 over pi cube here. So sometimes, just sometimes, people do the following. Sometimes people introduce, instead of 2 pi, like root square of 2 pi, now it will be cubic root square, 2 pi to the power 3 over 2. And then inverse transformation will be like this. Again, I do recommend you what you can do. It will be easier. I do recommend take this formula and take this formula if you can. Oh, for some reason I stopped sharing. I will go back now. Sorry, guys. Yeah, now we're sharing again. So basically what you can do, take this formula. and substitute it here. Substitute this formula.
Dr. Ackerman,
Yes, you don't see it?
for that equation you just circled, is that supposed to be a positive ikx in the exponent?
I believe, okay, maybe I believe so. Thank you, I believe so. Let me check. Yes. Yes. Sorry for misleading. Yes, it should be. Let me just take out of this notation. Yes, that's very good point. Yes, it just fully exactly. It's yes. When you do when we do inverse transformation, it should be definitely, yes, it should be definitely vice versa. Thank you. Yes, it will be like this, and it will be like this. Yes. And yeah, and that will be good practice for you again. So if you take this formula, substitute it above, and you should get 2 pi cube when you integrate all of them. So that's what we are doing. That's what we are doing, and why? Let me just go also on the screen. That's classical three-dimensional transformation. So now, what are the properties and what is interesting? So there is so-called convolution property. So basically, if I want to take, if let's say I have two functions, let's say I have function f and I have function g. Somehow, let's say one of them is velocity, another it's, let's say root mean square velocity or whatever. So, and let me say that I have the transformation. So what is nice to say that there is a so-called convolution property, which means that that if I make transformation of function f, let's see if I go here. So let's say I have function f, which I transform like this. And let's have I have function g, which I transform like this. So what is nice to see that product of the Fourier transformations will be transformation of a product. And that's really
transformation of the convolution.
Convolution, yes. Translation of convolution was given like this, exactly. So why we need it? Because this allows us to deal with correlation function. Remember we deal with the correlation function. Remember how we introduced correlation function. That it is, correlation function was all this integral that we are taking. Now, what is nice, we can deal with Fourier transformation of a correlation function. So basically, convolution is something that is a counterpart of correlation function. So in Fourier space, I have a counterpart of correlation function. So that's how we can introduce. So let's say this function phi, it will be transformation of a correlation function. So how a transformation of a correlation function look like? It should be this one, right? Basically, if I have limited space, I can calculate it like this, but that is a formula. That's what we have. And what is nice, then remember we discuss, so that is transformation, that is correlation function. So then remember what we know about correlation function are. What is I and j coefficients here? You remember that if I is equal to, if I and j are the same, we talk about diagonal elements, and what is this? What are these diagonal elements? These diagonal elements give you kinetic energy, specific kinetic energy, right? Turbulent kinetic energy. While elements when I is not equal to j show you dissipation. So the same story for transformation. So we will have this value, which is Fourier transformation of a correlation function. So if I is equal to j, you will have what? You will have kinetic energy. And that is nice to see. So basically formula below, I skipped some derivations here because we just stuck with them. But the formula below will show you what is specific kinetic, what is turbulent kinetic energy, how may it look like. Here you will see it. Let me take it. I'm sorry. Move it here. Okay, here it is. So look at this formula. What we have here, we have that if you, in principle, if you solve your problem in Fourier space, if you have Fourier analysis, what do you have? You need to integrate. So you need in K space to take this Fourier transform and integrate this value over all K's, over d cube K, and you will come to turbulent kinetic energy. So here, and please take a look here. So what is delta? Remember, delta is a Kronecker delta. It's a classical Kronecker delta, which is 1 if I is equal to j, and which is 0 otherwise, correct? So let's look what happens here. What happens if I is equal to j? If I is equal to j, in the right hand side you have k squared over k squared is 1 and gets out as it should. If I is not equal to j, then you have 0 here, and these values gives you dissipation. So when you summarize all of them, when I is equal to j will go out, and that's what we come to. Why I show you this formula? Now let's introduce something that we call spectral density, spectral energy density. Well, generally, and this is scalar value, so generally speaking, it depends on k. So it's like this. So we decided what? We decided that if I write, in general case, I can write ui. Okay, I also should do the following. I think it should be typo here. Let me just revise it. Yeah. So generally speaking, yes, definitely should be ui uj here, right? That makes sense. Which will mean that if I have I is equal to j, it will be kinetic energy. If I is not equal to j, it will be dissipation. So generally speaking, what we write here, we can describe it like this. So basically kinetic energy, and here, let me write just simple I here, because we say the following. So we say the following, that we express turbulent kinetic energy as set of bands in Fourier space. That is so-called renormalization analysis, how it happens. So basically what we say, that in Fourier space, let's say, if I transform my kinetic energy in Fourier space, I will have different levels of wave numbers, different levels of k. And this function E of k show the so-called spec, we call it spectral density. It's counterpart of energy corresponding to several wave numbers. Does it make sense for you? So that it is. It corresponds to wave numbers. And then if you integrate this over the entire wave space, you will come to your kinetic energy. That's spectral density. And if you integrate it in Fourier space, you can come back to our space. To illustrate it, I will show you something. And what I will show now, it will be related to reaction flow. So picture will be related to combustion, but it really describes turbulence. It's really related to what we're talking here. Let me show you something. I will do it now on my screen. Because you have, so what is, remember what is turbulence? In turbulence, you have many set of vortices, correct? You have it cannot be one coherent vortex. You have many vortices. So we can group these vortices, right? And each vortex will produce you something. Each vortex will produce some kind of value for you. Correct? So what does it mean for us? If you, I'm just one, oh, okay, I'm just opening another one. I want to just open some kind of diagram to show. Yeah, for instance, yeah, that's the best explanation here. Let's see. So what we are doing? So we talk about, let's say we have turbulent flow. Now don't consider difference between blue and red here, intensities. Let's say we have turbulent flow. That your turbulent flow consists of many vortices, big vortices, small vortices, and so on. So let's say I consider smallest vortices of size lambda of wave number k. They provide some corrugation of my flow. I count for it. And let's say these vortices are described by my spectral density, E of k. Then I have another vortices of larger size. They provide extra corrugation, and so on, so on, so on. When I integrate over all these vortices, I will have my total contribution of turbulence. Does it make sense? So here I grade my vortices by their wave number. So it means that I transform them into Fourier space and count over them in Fourier space. Let's go back to my slide here. So that's what we have here. Do you agree? This is your spectral density. So if I take fixed k number, let's say k is given. So I will consider vortices, and let's say A of k dk. I will consider set of vortices which have the wave number k all around. So this value, E of k, shows the contribution into turbulent energy created by wave numbers by vortices of wave number k. They consider larger vortices separately. They have different k, it will be another value here. Does it make sense for you? And if I integrate all of them in space, I will come to what? I will come actually back to my space and I will have turbulent kinetic energy. And this value can be expressed like this or like this. Does it make sense for you? Why I talk about like this? What's important here? Very simple. So it depends how this turbulent spectrum, it depends on the spectrum how your turbulence behave. And picture below shows the classical Kolmogorov scale that you talk about later. You already know from Kolmogorov scale, right? That you don't have small vortices, you don't have big vortices. And this picture will be discussed later. So you know that small vortices, and remember that what is K? K is 2 pi over lambda. It's inverse length scale. So larger scale corresponds to smallest numbers. So what I have here, I have E of k versus logarithm of k. So what does it mean here in the left-hand side? In the left-hand side, I have smallest wave numbers which correspond to big scale. So what happens, what does it mean that I have big scale? Big scale is larger than integral scale. Like imagine you sit in your room. Okay, so what is the largest integral scale you may attain? It's size of your room, correct? You cannot have vortex larger than your room. You are limited by it. So it means that if I consider very big vortices, very big scales, that is very small wave numbers, you understand that wave number is inverse to length scale, right? Then I'm here, nothing will be here, so there will be energy here. If I'm here, then vortices exist. Here I have different spectrum of vortices. I have spectrum vortices here. I have spectrum vortices here, here, and here. So here are my different vortices. There is all these cascades. And basically, that's what I have. Here, I don't have viscosity. I have only turbulence. But the less the vortices are, the more they dissipate. So it will be interplay between turbulence and viscosity, between kinetic energy and viscosity. And at some point here, I will have lambda, what we call lambda. Lambda is Kolmogorov, it's the Taylor microscale. Well, effect of viscosity and turbulence are balanced. And if you proceed more, your viscosity actually dominate over turbulence. And there is smallest scale, which corresponds to the largest wave number. That is Kolmogorov scale. After which all turbulence die, or turbulence disappear. So if my wave numbers are here, there is no turbulence anymore. So that it is. And do you understand now that what I have here is E of k versus k. And if I integrate this over k, so the surface area under this line will be what? The surface area will be turbulent kinetic energy. You integrate over vortices. And if I want to take one coherent vortex, let's say I have here and here. Let me try to annotate and draw something. So if I take one vortex, if I have another vortex. Okay, so this is a band of vortex or wave number k here, for instance, right? So here it is. So, and what I plotted here, this will be what? It will be E of k dk, correct? This is surface area that I just plotted here, correct? Here.
Yeah. Doctor, sorry. This plot, is it the plot of the expectation against against k or against logarithm of k? Which
This
one?
is not okay. Very good point. This is against logarithm k. In fact, this is logarithm k. So but yeah, what I plotted here. So you better use this versus k, but these numbers should be
Okay, logarithm scale.
logarithmic scale. So it should
Okay,
be
okay,
10
it's fine.
100, whatever.
Okay, sir.
That's good. That's good point. So basically, to have the proper dimension, it should be k, right? This
That's
to
fine, yeah.
interpret like this to have kinetic energy. And one more point, what I plotted here is that actually Kolmogorov spectrum. In reality, spectrum may be different. In reality, you may have something like this or whatever. We'll discuss it later. But that's the idea why we introduce this E of k. That's why we need it. That's why we use it. Because that is, so each band corresponds to one band in Fourier space. It's actually Fourier transform of your vortex, correct? So let me say like this, what is your turbulence? It's set of vortices. Vortices like this, that you have small vortices like this, for instance. You have big vortices like this. Maybe you have very small vortices like this. And something very big. So we classify them by size. And we consider this band corresponds to small vortices. This band will correspond to even smaller vortices. This band corresponds to largest vortexes because it's the integral scale, and this is very smallest, which die at Kolmogorov scale. And when we integrate over the entire spectrum, we will come to energy. And what is nice here to see is that so each band will be Fourier transform of particular coherent set of vortices. Does it make sense? That's what we have. So this is a basic idea about it. So, okay, now I should erase it again. Okay. So, why we need it and what? So, we need it to transform our equations. And that's what I want to show now. So, what equations are we going to transform? We need to transform continuity and Navier-Stokes equation. Yes? So, continuity, so let's see. So, how our continuity equation look like with constant density? That is our continuity equation, du or dxi is equal to 0. How it will look like in Fourier space? Very nice. In Fourier space, here it will be. Do you understand? So instead of taking derivative, instead of gradiential way, I will take, it will be this one. This will be this equation in Fourier space. Now, what about Navier-Stokes equation? Here is your general Navier-Stokes equation, how it look like, right? So what will happen? Let's look in Fourier space, and wave corresponds here. The wave will correspond here to not fluctuations, but to Fourier transform. So what I will have here? Time is time. So in Fourier space, derivative will take out. So instead of u, so let me say like this. So now I make Fourier transformation of this equation. Otherwise, I will have Fourier transformation of each term here. By the way, here is should be typo, I believe. Yeah, I think here it should be u like this. Yeah, because it's not viscosity, right? Yeah. Sorry. I see, there are all these typos, but when I was in the class, it was much easy to clean the blackboard. Right? Now it's hard. Yeah, it is. So let's see. This is our Navier-Stokes equation. So how is the transformation look like? Instead of time dependent, we will have time dependent derivative of Fourier transform. And which, if you have steady flow, you don't have this term, which is nice. This is our major term we play with, right? It's your nonlinear term, which we try to get rid. So that is nice. That we will deal with convolution. So UJ will have convolution of this term, and instead of taking d over dxi, I will have kj here, right? Why?
Yeah.
Because it will be just instead of gradient, I will have multiplied by k. Here, in contrast,
Doctor,
it will be j, right?
is it not minus ikj? Yeah. Okay, IKI. but there's a confusion between I for imaginary number and the index.
I see. You think it should be okay?
So maybe you should use two different.
Let me think. That's a good point. Let me think. Is it type or not? I should. Well, I will tell you. I should check this, but let me think. Let me think. Let me do it. I understand your point at least.
Maybe you can use numbers instead of that. I don't know.
So you say it should be minus. Well, here you can do minus.
I'm not sure. I might make mistake, but I want to check myself. Maybe it's minus.
Maybe. Okay. Well, we can check in your textbook. We will see. Okay. Well, I will check. I thank you for this comment. That's really nice. Yeah, maybe it should be minus here. Let me check in the book. Yeah, I will check. Okay, I will check for this. So basically, that's what we have, and we come to this. And so why we came to this? It's simply because that's what we have for pressure gradient. So remember how we deal with Laplace equation. With Laplace equation, we remember we wrote Poisson equation is actually and Laplace equation in this form. So in Fourier space, it will simply look like this. It will be that pressure wave. It will be density by all this case and convolution of ui and uj. So basically, why it's nice? So basically, in Fourier space, when you combine Navier-Stokes equation and continuity equation, you will come to the following set of equations. So this matrix T, it's like a counterpart of stress tensor. I don't want to write many formulas here, but basically what you will see, that is your set of equations. So equation of the top, that is actually what? This is general form of equation, which you have dissipation and we have kinetic energy. If you want to deal with kinetic energy only, it will be equation on the bottom. That's what you will have. It will be equation on the bottom. So that's what you're dealing with. Does it make sense? So that's basic idea how you transform. In terms of what sign is this, let me check now, because that's maybe you're right. That's maybe, let me actually check. I don't want to keep you confused. Okay. Let's look.
Yeah, I think it's positive. Eh?
We just positive. Why positive?
I just checked on the internet now.
Let me just open the notes. Because this, I tell you frankly, that when I derived basic theory, I derived it. This chapter I did not derive. Right. So let me, okay. So here, let me check. So this, no, it's plus, right?
Yeah, it's plus, yeah.
It's plus, it should be plus.
Yeah.
Let us check, but it should be plus. So there was no typo here. Okay, so that it is. So basically that is the basic idea about how it looks like. Does this make sense for you? Please ask me something at the moment. Please ask me. And please remember, so this formula, because we still have a little time, we still have about 15 minutes. So now I will tell you how we can approach with this something basic about Kolmogorov theory. What is this and how it looks. And again, like chapter 6 and 7 in your textbook is really too big for like fundamentals of turbulence. So I want you just to have basic idea and how it looks like. And when you already see this picture that is on my screen now, sorry for this frames, if you see this picture, you already realize why it's like this. So why we go like this. So how, that's classical Kolmogorov approach, and let me explain you how he arrived to it, what was there. So idea is very simple. Well, so what do we know about Kolmogorov approach? So let me say like this, what do you know about turbulence already? I just discussed with you. So we know about turbulence that we have several scales. What do we know about turbulence? We know that we have different set, or we have different set of vortices, correct? We have different set of vortices. We already know that, like, we have big vortex, we have smaller vortex, and so on, right? So if you consider in terms of spectrum, let's say like big vortex, smaller vortex, smaller vortex, smaller vortex, smaller vortex, okay? So why we don't have vortex big larger than this one? Because this is your characteristic length scale. That's how we call it L, integral scale, right? And this scale, your vortices dominate, and this is your domain, your configuration doesn't allow to go more. Now, and definitely what you have here. So wave number corresponding to this wavelength will be what we call K. We can call it KL, which will be 2 pi. Sorry for my typing like this, but it's if I type the text, it will be longer. Or lambda, or let's say over L. Okay. Now, at some point here, we have so-called Taylor microscale, right? What is Taylor microscale lambda? Remember, we got it in chapter 3, like first derivative and expansion on small parameters. And here, viscosity and turbulence will be about the same. So we will have K lambda. And eventually we come to a smaller scale. You know that at some point, if your scale is really small, this kind of vortex will die very fast. It will die because of thermal conduction, thermal dissipation. So this will be so-called, we can call it Kolmogorov scale. Typically we call it eta. And here you'll have that K mu, it will be 2 pi over eta.
Dr. Agarpan,
Yes, please. Yes.
I have one question. Like in this slide, the first equation you are showing for the turbulent kinetic energy.
Yes.
So you are integrating at the function of a wave number, but your integral, like the limits is from minus infinity to infinity.
Very good. Okay. Yes, that's okay. Very, very good point. Yes, definitely. In reality, is the following. Okay, very good point. Yeah, I want to make it simpler, but you catch me. That's true. So, very good point. In reality, let me just close it here. In reality, it should be like this. And in reality, it should be actually like this. Very good point. In reality, it should be like this. And here it will be actually function of vector k. Does that make sense? In reality, because and k, you have k1, k2, k3, it goes. But, and yes, it will be like this. And in reality, it should be j here. And if you have j here, your correlation function can actually be positive or negative, right? So it will be ij here, if you take subscript. Now, if we talk about, that's how it is, and you actually integrate for over space with minus and plus. Now, if you are interested in kinetic energy only, your E value should be positive only. So we will take only diagonal elements here. Now, you know that kinetic energy is a squared term. So it should be symmetric with respect to K. So the wave number K plus and K minus should be exactly the same, right? In terms of, that's why what we have in reality, we took only positive K numbers here. We do it like this. And here, exactly, you are right. It should be from zero.
Infinity to 0.
It should be from 0.
Yeah.
Or, if to be very more accurate, it should be to I should write like K maximal here, right?
Yeah. Yeah.
And here I should write K minimal.
Yeah.
Does it make sense?
Yeah.
Yes,
Now it makes sense. Sorry for I was a
No,
little
no,
bit
it's
confused.
okay. It's very good. It's very good that you mentioned this. So, but why I put this way module here, absolute value? Because it's your result. It's kinetic energy. So it should not depend on direction. It should depend on squares. It should depend on K squared. It should depend on absolute value of K, right? And absolute value. So if I have vortex, like this, and if I have vortex like this, from the kinetic energy, it's exactly the same vortex. It's direct. Here wave number is directed to me, here it's directed to you, like from me. I would say to you, provided that you are from that side of the screen, but you are from this side, sorry. But you understand that over the surface and from the surface. So key point that these vortices, in terms of energy, not in terms of direction, in terms of energy, are the same. So, and that's classical approach that Kolmogorov uses, that your energy does not know about direction. Your energy knows only absolute value. So it will be like this. So, and what is K minimal? Here that I plotted. What is K minimal?
It's Kolmogorov scale.
What do you say?
It's corresponding to Kolmogorov scale.
Think again. Kolmogorov scale. So
Oh, sorry. I mean the integral scale, because
exactly. So that's actually K. Yeah, that's what that's actually KL, correct?
Yeah.
That's that's very important to remember, because sometimes people see vice versa. So, and this is K Kolmogorov.
Yeah.
Let me say Kolmogorov, because if I write mu, it will be not seen, right?
Okay, eta.
Yes, but if I write eta, you will not see it here, believe me.
Okay.
K N K N, something like this, yeah. Eta will not be seen here. Yes, that is K. Let's say K Kolmogorov like this. Yes, but that's important. So you go from, that's important that you go from small scales to big scales, right? And if you look at this diagram, so this smallest K corresponds to larger size.
Yeah.
This larger size corresponds to smallest K. And that's why it decreases with K, because of energy cascade. You go from small scales to big scales. So your energy goes like this, not vice versa, not like this, it goes down. That's key point of 3D features, right? Does it make sense?
Yeah.
So that's idea. So that's what we know ourselves anyway. So what Kolmogorov did, what he developed, and he did very simple. So based on this knowledge, he says that okay, he wanted to find this how this E of K behaves. So what is dependence E of K? How this function look like? And you already know that the answer will be power 5 minus 3. But he did classical dimensional analysis. I think you know what is dimensional analysis, right? You write power in some, you write some parameters and some dependence, some functions, and try to combine them to see what power dependence is. I think if you take any fluid mechanics class like 532 or even undergraduate, you deal with this dimensional analysis. So that's how, what did Kolmogorov? He says that what we know about turbulence. Turbulence should depend on 3 parameters. It's actually balance of what? Of turbulent dissipation energy, of dissipation, and of viscosity, right? So it is 2 parameters that should play the role, dissipation rate and viscosity. And he managed to express all these features in these values as follows. I just show it here simply. Let's see. So what Kolmogorov theory says, that you have, okay, I should actually erase this. Yeah, like a blackboard, interesting. Okay, so what are we going to do here? So basically, so what we have? We have viscosity and we have energy dissipation. So what are the units of energy dissipation? Do you see my screen here? Let me increase it a little bit, yeah? So I think like this. So basically, what are the units of viscosity coefficient? By order of magnitude, that will be length scale multiplied by velocity, correct?
Yeah.
It's very easy to check because what is Reynolds number? Reynolds number is the ratio. It will be length scale or velocity divided by viscosity. So it should be length or velocity at all these transfer coefficients. So if you take about their dimension, it will be what? It will be length squared over time, and it will be meter squared over second. So that is dimension of viscosity. Everybody understands it? Yes?
Yeah.
Okay. Everybody else? I believe so. Another value. So what we also have? So we have this, what do we have because of viscosity? We have this dissipation. And remember viscous dissipation, remember this term? We talk about this. And we derived it in our basic theory. So how it looks like, what is the unit of this dissipation? It will be du over dx squared. And what is value of this? And multiply by viscosity. So what is the value of this? This value is velocity over scale, it will be 1 over time, and this is viscosity. So if you calculate it with viscosity over time squared, it will be meter squared over second cube. Or otherwise, it will be velocity divided by time, as it should be. Do you agree?
Yeah.
Very good. It's very simple, you can just reproduce it, but it's very good practice. Typically, I do it in the class on the screen, but it's very good practice here. So what Kolmogorov told that all parameters like Kolmogorov scale, Kolmogorov time, Kolmogorov characteristic velocity should be obtained by dimensional analysis. So he says that, okay, he says that let me introduce scale named after me. Me is Kolmogorov. So let me introduce Kolmogorov scale. It will be a scale at which vortices die. Okay? So he says this scale should depend on what? It should depend on viscosity. And it should depend on dissipation. Do you understand this? Do you agree with this?
Yeah.
And then dimensional analysis. So let's hit all like this. Let me look for my solution in the following form. Let me look for my solution in the form like this. Like mu to the power alpha and epsilon to the power beta. When alpha is beta are some unknown coefficients that I want to find. And then we employ analysis. So what I have here, I have viscosity to the power alpha. So let me substitute. So I will take viscosity, which is, what is viscosity? It's length over time scale. Here it is. Is it viscosity? Do you agree that this is viscosity?
Yeah.
What is this? This is
That's
viscosity.
L square per T. That's a length square over time.
Yes?
But
Okay, let me say like this. So this is viscosity, right?
yeah.
This is viscosity like it is now, right? If
Yeah.
I multiply by alpha, it will be viscosity to the power alpha, correct?
Yeah.
Yep.
And what is this? What is
Yeah,
L
yeah.
squared over C? If I remove this, what I will have here? Okay, let me do like this. This all new teaching skills I practice now. Yeah, it's good that I'm tenured now. It's not my critical year for promotion when I test all the skills. But anyway, yeah, somebody who going now for promotion, it may be terrible time, I believe. Anyway, so okay, so that it is. If I remove like this, so this is my epsilon. So if I put like this, that will be what? This will be my viscosity. This will be my term here. So that's what I have. So, and altogether, do you agree that it will be nu to the power alpha, epsilon to the power beta? And if I calculate together, it will be this one. Now, what is this? So I have length to the power 2 alpha plus b, 2 plus 2 beta, and time 3 alpha plus b. Okay?
Yeah.
Now, and that is what? That is Kolmogorov scale. It's length scale, correct?
Yeah.
Yes. So, what does it mean that a length scale? It means that at the end I should have length to power which? Power 1. And time to power which? 0. It should be, time should get out. So
Yeah.
I will have this expression and this one. Do you agree with this?
Yeah.
It's dimensional analysis. So this combination should give me length to the power 1 and time to the power 0. I don't know. I should mute somebody. I think here. Okay. So that it is. Do you agree with this?
Yeah.
Okay, so from here, I have set system of equations to unknown to equations to unknown alpha and beta, and from here I find what is alpha and what is beta. Is it easy?
Yeah.
So from here you will, and then from here I will see that my alpha is 3/4, my beta is 1/4, and I will have expression for my Kolmogorov scale. Here it is. So I will have that my Kolmogorov scale should be like this. Again, you may say, why not two of these values? It's turbulence, people, you know, it's turbulence. Here we do everything by order of magnitude. So that is, all this dimension analysis is by order of magnitude. If I write coefficient 5 here, it will be 5 here. If I have 5 here. If I write coefficient 0.1, it will be 0.1, but that's dimensional analysis. And that's how we arrive. So that's, yeah,
So
please.
Dr. Ackerman, one question. So it might be like a silly thought, but while Kolmogorov tried to like find the relation between this scale with viscosity and dissipation rate, so I was thinking that dissipation rate itself caused this kinematic viscosity term over. I mean, like this viscosity term over here.
Yeah, it's still here. Yes, it's still.
Yeah. So, but why is he? In addition to that, why is he still using like b to the power alpha times epsilon times beta? Because
Okay.
epsilon itself contains the viscosity, right?
Well, okay, okay. I will tell you. I try to simplify it here. Let me say. I will explain you. So what Kolmogorov actually did himself, he introduced another parameter that we did not use. So let me say instead of epsilon, let me call it epsilon1. Okay.
Okay.
For epsilon1, he used like this, and he introduced this formula. So he deal with velocity. So his scale dissipation.
Okay.
So what he actually did, and this epsilon, and you may realize that epsilon has dimension of what? Not of viscosity, it will be just velocity, it will be just 1/time, right? It will be, if I calculate, it will be
per second square.
1/second, I believe, right?
Yeah, second square.
Yes. Okay. Yeah. It will be 1/second squared. Okay.
Yeah.
It's E1. It's another dissipation, right? So here, well, you can use E1. Okay.
Okay. Yeah.
And then you will come instead of in here. You will have instead of this, you will have 1/3/2 beta. Then.
Yeah.
So after this, your alpha and beta will be different, but if you want to have E1, but you eventually come to the same formula here. If you want to have E1, it will be another power here.
Okay.
Okay, does it make sense?
Yeah, it makes sense.
I did not introduce, but that's very good point. I did not introduce this even in our class, so that's we apply with this. But that's what Kolmogorov actually did. Because epsilon dissipation is actually not only proportional to kinematic viscosity, it's also proportional to this term.
Yeah.
And that's make it conceptually different. Because viscosity is typically constant.
Yeah.
While this depends on space and velocity. It's a function. Anyway, does it make sense for everyone? So let me remove this and come back to what I did before.
Sorry for this.
No. It's very good. It's very okay. It's really because that's what we try to learn. So that's how he derived it. That's how he derived. So basically, that is our formula eventually. So that's for this. But now, that's Kolmogorov scale. But there are also other parameters. No. In addition to Kolmogorov scale, he introduced a concept of Kolmogorov time. What is Kolmogorov time? It's actually it can be defined in two ways. It's actually characteristic time, how long Kolmogorov vortex lives, or it's characteristic time of body propagation through Kolmogorov cascade. So again, he defined it by order of magnitude. So the same dimensional analysis. So he says that let me Kolmogorov time, again, it should be function of viscosity and dissipation. Okay? So now again, the same story. He is looking for P and Q based on dimensional analysis. Does it make sense for you?
Yeah.
So we substituted here, and here we have the following. So you agree that why he come to this? Because this is L, it will be L to 2 pi plus 2q, pi plus 3q. And based on this analysis, he calculated the following. He calculated that P is equal to minus Q, and it will be 1/2. and that he arrives to this formula for characteristic Kolmogorov time. Okay?
Yeah.
Does it make sense for you? Also, there is velocity scale. There is velocity scale. And basically, there are two ways how to find velocity. To check yourself, typically what I do in the class, the same story. You can look for velocity in the same form. Like you will write that your velocity, you can do it like this. You can write that your velocity, and here let's see v, it will be something like, I don't know, not PQ, let's say m and n, something like this. And again, you can proceed and find this coefficient m and n in the same manner, right? Okay, and find m and n like we did here, right? You substitute, it will be L to the power m and e to the q to the power n minus m and so on. But there is an easy way to do it. You can simply take, what is my velocity scale? It will be length scale over time scale. What is my length scale? It's my Kolmogorov scale. What is my time scale? It's my Kolmogorov time. So the ratio will give me characteristic velocity scale. It's very simple, correct? So why we need it? Then what Kolmogorov did? He finds the expression for the spectral density. It's the same because he knows that what is spectral density. Your spectral density should depend on what? Should it depend on K? Yes, it should depend. Should it depend on dissipation? Yes, it should. So he wrote that let it be some kind, let it be proportional. Let it be proportional to this one. I use Word file document here because when I type in PowerPoint, I will never save it after this. It's because of notation. So I use a Word here. So he looked for this solution, or he looked like this, and found this A and B, what they should be. So B should be 5 minus 5 over 3, alpha is 2 over 3. And this allows him to come to the classical formula. So that it is. So these are outputs of the Kolmogorov theory. He says that this is Kolmogorov time, this is characteristic velocity, this is Kolmogorov, let me do it here. This is Kolmogorov scale. And that is how it looks like. So that's what he demonstrated, that your E of K, your spectral density that you just derived in Fourier space, is like this. It depends on dissipation to the 2 over 3 power, and it behaves like K 5 minus 3. Here is the dependence. And now that's why we wrote it in logarithmic scale. That is the formula. Because in semi-logarithmic scale, log scale, in fact, what happens here? This is straight, it's like just linear line. And this angle of this line will be minus 5 over 3, right? In logarithmic scale, your exponential line is linear, and angular coefficients will be minus 5 over 3. It should be minus. Why it's minus? Because you go from small scales to big scales. Remember how we wrote? Remember when you integrate here, where it was? When you integrated, not here, it was in my PowerPoint, right? So yeah, when we integrated here, remember we integrated from from what? From K minimal to K maximal, from largest wave number, from smallest wave number to Kolmogorov wave number. So in reality, you go from larger scale to small scale. That's why it goes. You go in different way because this is negative power dependence. If you go from small scale to big scales, you will go linearly like this. You understand that what we see here, right? What you see here is it. It's like a straight line. And what is angular coefficients of this straight line? It's power minus 5 over 3. It's negative coefficient because it declines.
Mm-hmm.
Everybody understands this?
Yeah.
So that is classical Kolmogorov outcome, and that is his theory. That's what it is. That's how it goes. So here you're in between Kolmogorov scale, which is 2 pi over Kolmogorov wave. Here we have Kolmogorov wave number, which is 2 pi over eta, and here you have integral wave number, which is lambda minus 1. And spectral density can be calculated like this. You go from K1 to K2, or like say you go from 0 to infinity, you go for, and that's exactly what I write here is exactly what Ansan mentioned. So if I want to calculate my total, let's say kinetic energy, it should be capital K here. It should be turbulent kinetic energy. If you calculate, it will be the following, right? You integrate it, So you should integrate actually from 0 to infinity. But in reality, you integrate it from Kolmogorov, from integral to Kolmogorov scale, because there is nothing below Kolmogorov integral wave number, and there is nothing above Kolmogorov wave number, right? All these big wave numbers are empty because small vortices die. All these big vortices don't exist because you are limited by your size. And if you substitute this Kolmogorov formula, into this equation, that's how you will arrive to the expression. That's how it will look like, and you will see that your kinetic energy will be as a function of integral scale only. That it is. That's how it looks like. Okay, I will stop at this point, and we will keep talking a little bit about Kolmogorov scale at next lecture, and I will put the record of it online. But does it make sense for you? Do you agree with this? Does it make sense?
Yeah.
Okay. So again, I will post. Okay, I think what I will do, I will split in video discussion about Kolmogorov and discussion about Fourier transformation and previous lecture. So I will post it. So
Dr. Ackerman, I was wondering, like, all these formula are generated using the dimensional analysis. So did the Kolmogorov did some kind of validation for this thing?
well, yes. Okay. Answer is the following. Kolmogorov did validation, and that's how he found his Kolmogorov constant because of validation. So let's see. If you write this formula, what you have unknown value C, right?
Yeah.
So, but he got this trend, and from experiments, he got this coefficient C.
Okay.
But you are definitely right, and that's what actually I will keep talk a little bit next time. That now very seldom people use Kolmogorov approach because it's really like I like a concept of spherical horse in a vacuum. It's very good when you do something new, when you start new research in nanoscience, in info, in bio, and whatever. Then you can do any kind of approach you want, do something very elegant, very nice, and you are the pioneer. So what Kolmogorov derived, any of us can do it right now by hands, right? But he did it first, and he is genius. He did it.
Yeah.
But of course, you are absolutely right. Of course, the approach used here, that you just dimension analysis, are not very accurate. There are ways how to, and now people use much more powerful formulas. For instance, and that's what I'm going to talk to you. That very simple way to there are many. So what people do now, they use much more complex formulas instead of Kolmogorov. And one of them is in Peter's book and Stephen Pope's book. Like you can use spectrum like this. So what you may see here is adjustment of Kolmogorov spectrum. So Steve Pope, he's a professor in University of Cornell in Ithaca, and he's very well known for his approaches to large eddy simulations. He actually introduced statistics in large eddy simulations, PDF-less approach. So one of his approaches, it's modified Kolmogorov spectrum. So you may look if you look at the slide, you will see what's happening here. So left-hand side, it's what is here. It's exactly Kolmogorov spectrum. But what he needs, he introduced correction functions. He says that I want to, because what you may say about Kolmogorov spectrum? If you take a look here at classical Kolmogorov diagram, and if you take a look at this picture, so when do we have when do we have the straight line? If you put it here, like that's what I did. Let me.
I remember that.
Yeah, if you do it like straight line. So definitely the straight line works very in the middle of your spectrum. Definitely this approach, this straight line does not work here and does not work here, right? So basically when you come very close to Kolmogorov scale, when you come very close to integral scale, it does not work. Dimensional analysis like this work when you are far away in between them. So otherwise it works when lambda is much less than integral scale and much larger than Kolmogorov scale. Right? When you approach them, it would not work. So what people do then? Then people, I want to show it here. Yeah. So maybe I should remove this annotation, erase it again. Yes. So what people do then? Let me see here. I try to convert the notes in Word format, but it did not work very well. So people introduce correction factors. So in addition to Kolmogorov scale, they say that, okay, I want to have a function which shows two limits of integral scale and limit of Kolmogorov scale. So he multiplied Kolmogorov spectral density on this function and on this function. And says that this function, he showed integral scale. He found this empirical correlation like this with some coefficient beta. I don't want to come in many details, but what he demonstrated that this function should be 1 everywhere except for near integral scale. Does it make sense for you?
Yeah.
And this function should be 1 everywhere except for Kolmogorov scale. But at Kolmogorov scale, it shows correction. So this is better approach which shows that's what people may use. Does it make sense for you?
Yeah.
That's what something. Also, if you remember, you attend my combustion class, right? In combustion class, remember we use Pashoy approach, Yakut approach, Bychkov approach, Chudry approach. Basically, the idea was like this: again, that this function epsilon of k is too simplified. We had much more complex expression here, which included combustion parameters, reacting flows parameters, and that makes sense because if you have combustion, in addition to Kolmogorov scale, you have flame thickness, and for any other geometry, if you have nanopipes, if you have nanotube, definitely size of your nanotube should play the role, not just entry pass. Okay, does it make sense?
Yeah, thank you so much.
Okay, well, yeah, well, thank you for questions because it means that something that I explained is still okay. Okay, so please, okay, so let me write up for today if there are no more questions. Let me, and I will post everything. I will post all these results. Okay.
Okay, thank you.
So I will post it, and I will see you on the 3 lectures left. I will see you on Thursday, and also I will recommend you to watch the videos that I sent you at very first lecture because now I think you will be much more familiar with it. Right? Right? Okay. Thank you.
Thank you.
Yep. Good luck. Okay. Okay. Let me stop sharing screen and let me end up. Some people say okay. Okay, and let me stop now.